Modern neural networks are trained across massive server clusters, where thousands of synchronized pulses of electricity represent the calculation of billions of parameters. This reality creates a feedback cycle, where infrastructure tools and research concepts directly shape one another. Developers often favor ideas that are simple to implement within existing software and hardware constraints. This table highlights the massive throughput disparity since 2004. An Intel Core i9 provides 640 gigaflops, while an NVIDIA RTX 3090 reaches 35 teraflops. Economic value follows this curve. CPU efficiency remained flat, but GPU efficiency reached 38 gigaflops per dollar with tensor cores. The gap exists because CPUs are designed for serial execution. They dedicate significant silicon area to large control units and cache layers, which manage branch prediction and the complex if-else logic required for general-purpose software. Deep learning algorithms bypass the need for this complex branching. They rely on deterministic, static mathematical sequences, where every operation is independent and uniform. Because neural networks use these predictable sequences, we can strip away the general-purpose control logic and use thousands of smaller, parallel cores to execute them. This biases research toward models that fit the parallel processing constraints of current hardware. On the surface of the chip, a single neural network layer is a collection of weighted connections between input and output nodes. Standard procedural code uses nested for loops to calculate these node activations one by one. This causes repeated jumps in instruction memory, resulting in slow execution speeds that bottleneck research. To increase speed, we express these operations as direct matrix multiplication using single instruction multiple data, or SIMD. This allows the hardware to execute the same operation across thousands of data points at once. Software like CUDA handles this mapping by assigning every parallel thread a unique global index. The thread uses its block and grid coordinates to identify exactly which cell in the weight matrix it is responsible for calculating. Modern frameworks abstract mathematical complexity using reverse-mode automatic differentiation. Instead of humans deriving functions by hand, the software tracks operations dynamically. The system records a computation graph during the forward pass, storing intermediate variables. During the backward pass, it traverses this graph in reverse, applying the chain rule to automatically evaluate exact gradients for every learnable weight. Automating both the calculus and the memory allocation allows for rapid prototyping of complex mathematical models. It shields the developer from the underlying execution pipelines until the model grows too large for a single device. Loading weight parameters from memory takes time. If we only process one input vector at a time, the GPU spends more time moving data than it does performing calculations. Batching solves this by stacking multiple input vectors horizontally into a single matrix. This allows the hardware to reuse the exact same loaded weight matrix across all inputs in the batch simultaneously. While larger batches increase hardware utilization and total throughput, they also demand more memory. The system must store the intermediate activation values for every single sample in the batch during the forward pass. A small batch might only require a few megabytes, but as the batch size increases to maximize GPU efficiency, the memory footprint expands until it consumes the entire available video RAM. This creates the VRAM wall. When a model requires 80 gigabytes for its parameters and optimizer states, it strictly exceeds the physical 24 or 40 gigabyte capacity of a single accelerator. To scale past this wall, the infrastructure must be redesigned to break the boundaries of a single silicon chip and distribute the load across multiple machines. Distributing a model across several nodes requires coordinating calculations over a network. The most common strategy is data parallelism, where the mini-batch is split into chunks, but the entire model architecture is duplicated across every GPU in the cluster. This requires constant synchronization. After each GPU computes its local gradients, they are gathered and combined using an all-reduce operation to ensure every replica updates its weights identically. However, data parallelism cannot train models that don't fit on a single GPU. Since every node must store a full 120 gigabyte copy of the model, the memory limit of the individual card remains the ceiling. Model parallelism attempts to fix this by splitting the layers of the network sequentially across different GPUs, placing the first layers on GPU 0 and the final layers on GPU 1. But naive model parallelism creates a pipeline bubble. In this timeline, you can see that devices 1, 2, and 3 sit idle, while device 0 processes the initial forward pass. They cannot begin their work until they receive the activations from the upstream GPU. In a 4-device setup, each GPU spends roughly 75% of its time idle. To mitigate this, we use micro-batching. By splitting the main batch into smaller sub-batches, we can overlap the forward and backward passes. This formula shows that as the number of micro-batches increases relative to the number of devices, the idle bubble fraction shrinks. Naive distribution either wastes memory through duplication or wastes compute through idle time. Modern scaling requires a more granular approach to partitioning the model. The Zero Redundancy Optimizer, or ZERO, eliminates memory redundancy by fracturing the model states across the GPUs rather than duplicating them. In Stage 3 partitioning, the total memory footprint, including parameters, gradients, and optimizer states, is divided by the number of GPUs in the cluster. For a 7.5 billion parameter model, this reduces the memory requirement from GPU from 120 gigabytes down to just 1.9 gigabytes when distributed across 64 GPUs. The GPUs dynamically fetch these partitioned parameters over the network during the forward pass and release them immediately after, keeping the memory footprint low throughout execution. While Zero manages memory, tensor parallelism manages computation by splitting the math of a single matrix operation across multiple GPUs at once. This involves slicing the first weight matrix vertically into column-wise partitions and the second matrix horizontally into row-wise partitions, assigning each slice to a different GPU. Each GPU independently computes its subset of the linear projection in parallel, without needing to communicate during the activation step. These parallel results converge at an all-reduced summation operator, where the outputs from all GPUs are combined before the final dropout is applied. By mathematically slicing these operations and dynamically partitioning optimizer states, we bypass the physical memory wall of a single GPU, allowing massive models to fit across a cluster. Keeping these distributed segments synchronized requires high-speed interconnects, as every synchronization step adds communication latency to the training pipeline. There is no single universal strategy. Selecting a parallelization method is a balancing act between the size of the model, the available video RAM, and the bandwidth of the network. The decision tree begins with a simple check. Does the model fit on a single GPU? For models that fit, we use distributed data parallelism for speed. If the model exceeds the memory of one card, we apply Zero, pipeline, or tensor parallelism to distribute the layers across the local GPUs. At the cluster scale, we often use 3D parallelism, combining pipeline, tensor, and data parallelization to reduce communication overhead across physical network links, even though it requires significantly more complex code. This infrastructure provides the foundation for rapid experimentation. Just as massive compute foundations enable new ideas, the physical constraints of the hardware continue to shape the mathematical concepts of the future.